we are already adding lots of error, and the last thing that we want is that we add some extra artifacts on top of it, right? So in order to remove it, so in order to remove it, we don't use the bicubic. So bicubic is bad because it causes this aliasing. So we understand that the aliasing is happening because of this high frequency. Another thing that we can do is you have a fixed camera. I mean fixed camera in the sense that your Nyquist rate is fixed. The person in front of you which you are interviewing is the president. You cannot tell the president, change the shirt. And you know that if you are showing this broadcast to TV, then next day the president can call you and complain that why my shirt was looking like that. Can you tell me a solution that I can do? You cannot tell the president, change your shirt. And you cannot broadcast it, but you have to broadcast it because you want to earn money. What is the solution that comes in your mind?
Don't record the shirt.
Don't record the shirt is one alternative, but then it will be that they are recording the mouth of the person. I think you would prefer to have this shirt be the problem then. So let's put it in this form. So let's put the question in this form. What was the reason? What was the reason for the problem? What was causing this aliasing?
Low sample rate.
A low sample rate, paraphrase it. I mean, the problem was not my camera. The problem was something else.
The shirt.
What about the shirt? Razan?
Less hue, less color, less light,
No.
high frequency.
Yes, the problem was the high frequencies that I had in there. Like I had the shirt and there are lots of high frequency because of the texture that I have. And I have the camera which is fixed Nyquist rate. Because it is fixed, I know I can calculate what is the maximum frequency that I have. So, what can I do? I know that the problem is in the shirt because there are lots of high frequencies.
Make it out of zoom a bit.
No?
Maybe you can filter out.
Yes, I can filter out so many of the high frequencies. Remember, our eye cannot understand so many of the frequencies. In other words, I am looking at your picture, okay? And then inside the picture, we know hair has lots of high frequencies because it has lots of details. But if I kill all those details of the hair, and I show you the image, we cannot understand that the details of the hairs are gone. We are significantly reduce the number of high frequencies that we have. Like maybe your highest frequency will be dropped by 1,000 times, but you do not see it. So what we can do is that we can always see if the frequency is much bigger than the frequency that we had. I can put a filter. They put a filter actually on top of the camera or at the back end, and they kill all those high frequencies, so we don't have any aliasing problem. So this is another solution. This solution that I talk, we will come back to it, and we will talk about the frequency, the filters which we can use in order to kill these high frequencies. Okay? So keep that one in your mind because I will ask this question again later. By later, I mean maybe in 1 month's time. Now, some warning. In the next few slides, which you are not responsible, we will talk about the mathematical representation of nearest neighbor, bilinear and bicubic interpolations, in order to give you an idea how they work. With one of my PhD students, actually we have developed a new kernel for interpolation, which we are using it, and it seems that it works better than any other kernels that we have at the moment for interpolation. So the reason that I show it to you is that maybe some of you will inspire and wants to work on works like this, developing a mathematical curve or kernel which helps you. Now, the nearest neighbor, as the name stands, I look at my nearest neighbor, so it's like that I have a uniform distribution shape. So I will put it on the pixel that I want, and I see that who is my neighbor, and whatever is my neighbor, I will copy the same values, right? So I don't do any calculation. I just simply copy whatever is satisfied in here, right? This is the conditions that we have. Now in the bilinear, what happens, I am defining a linear equation in order to tell me that what should be the pixel value that I am looking for. So if it satisfies the conditions that I have, I just put the value of the x and I calculate what should be the new values that I wanted to replace it into my function. And here you can see what happens with the bicubic. And as I told you that we have a third order polynomial. That's why it's called bicubic. We have a third order polynomial in order to calculate what should be the values inside our function. Now, in general, your homework, you will be responsible for bicubic, you will be responsible for bilinear, you will be responsible for nearest neighbor. In the exam, you will be able, you have to be able to judge what are the differences and what are the advantage or disadvantage of them. But apart from these, we have another type of interpolation which is called SP-line interpolation. And SP-line interpolation, as you can see, again, it is of the third order, so it's very similar to bicubic. It is a slightly better, but we can always come up with some images that bilinear is better. And here you can see the different type of filters or kernels that we are using in order to find out the result of each of them. Interpolation techniques. Now, in our book, we had a very nice image. Which gives us what is the result of interpolation by using bicubic, bilinear, SP-line, and bicubic. As you notice, we have this blocking effect. I mean, you have the lecture notes. You can always zoom and see. And as we are using the bicubic or SP-line, the image will be sharper. We can see more details. Now, another very useful way of making interpolation is by use of this function, which is called sinc function. So let's see, Fatana, what is the sinc function? Have you heard of this function, sine x divided by x? It's called sinc function. It looks like this, as you can see, the black one. And there is something very special about this function. Do you know what's special about this function? It's a very useful function in signal processing. It's one of, I think, most frequently used function. But again, because we use it quite a lot, it means it never exists. It's a function which does not exist. We wish that we had the function like this, because if we have a function like this, so many of so-called ideal filters or ideal designs would exist. They do not exist on the real life because this function does not exist. And who wants to tell me why this function does not exist?
You can't use it when t is 0.
When x is 0. But we can calculate this one. Limit of x goes to 0 of sinc x, which is the limit x goes to 0 of sine x over x is equal to 1. You can use Hospital rule in order to find it out. But, as Andres mentioned, sinc 0 does not exist. The limit goes to 1, but it does not exist. We put it 1, we draw it, but it does not exist. Because it does not exist, we don't have it. So, again, this is a very good kernel. Look at the shape. Look at the shape. It is it a periodic signal? It is not periodic signal, but it's kind of periodic signal. It's periodic in the sense that you can see where the zeros are happening. I mean, come on, we have sine x, so we see that it should have then the potential of being periodic. But we know that as we are going towards infinity, these ripples, these wings start to die. So the magnitude starts to go, to become smaller. So it's not periodic by the definition of periodic. But we understand that it repeats itself, like at least occurring of the zeros or going up and downs based on some period. So this is the function sinc. Now, Be ready, I want to ask you a question. I had an image, and the image looks like this. And this is the black part. And I made it bigger, as you can see in the slides. I made it bigger, and then we have nearest neighbor, which is causing this steps. What's your name?
Akil. Akil.
Akil will tell us why do we have these steps, whereas here I had a very straight line. Yes, aliasing, but use another word for it. Why do we have aliasing?
Frequency.
No. Why? Which method is this one?
Nearest neighbor.
Yes, because it's nearest neighbor, we have the aliasing. What was the other word which we use for aliasing? Blocking. So we have this blocking effect. Because of the blocking effect, it means that this is straight line, we start to have some steps. Okay? So why we have it is because of the nature of the nearest neighbor. Okay? Now, Aygul will tell us this. That look at the sink. Sink is very nice, right? But Aygul only will tell me, why do I have bright lines, dark lines? Bright lines, dark lines. And actually, if you have a computer, you will see that we have dark lines, brighter lines. So it's like that we have this dark and bright all over. Why?
This is the limit point,
This is what?
the point that it gets to 0
No.
for every.
What's your name?
Vadim.
Okay, Vadim maybe will tell us.
Probably because of the form of the sink.
Yes, exactly. Look at the sink. We have valley, peaks. Valley, peaks. Valley means that it will become dark, darker than what it's supposed to be. Peak means I will make it brighter because I'm multiplying with some magnitude, right? It's not all one. So that is why we have these peaks, valleys, peaks, valleys. Okay? So this is the problem with the sink. Again, keep this one in your mind because we will see this sink later, we will see this problem later, and I will ask the same question. And it's called ringing effect. Right? We start to have lots of rings around. Now, Ozan will tell me that why do I have this one, this dark line here in BSP?
Can you return the formula?
You don't need the formula, I can tell you, because you have the answer here. Yeah, look at the blue one. Okay, it's bicubic and BISP is very similar to each other. Look what happens. I have one valley in here. Only one valley. So only one valley means that I have one dark line in here or in here, but afterwards it's okay. Afterwards it's okay. What about bilinear? Why I don't have any ringing effect in here?
Because it's had a straight
Yeah,
line.
because it's two lines, come here and afterwards I go to 0. In other words, I do not go to negative bar. In other words, I do not have any valley. If you have a valley, it means that you are expecting to see some darkness. If you have a peak, you are expecting to have some brightness. Look here, I do not have any peak anymore, right? For let's say by cubic or BSP line. What happens after this valley? I have all zeros. That's why that after this dark part, I do not have the bright parts anymore. I have the whatever the value of the pixel intensity was. Okay? So these are the things that if I give the image like this in the exam to you, I'm expecting you to analyze and explain it. Right? Okay. This is what we talk. We said that we have something which is called the Nyquist rate. If you sample with less than Nyquist rate, you are okay. But what happens, you have something which is called aliasing. You will not be able to reconstruct your image or your signal back exactly as it is. You can reconstruct it, but you will start to have lots of artifacts. Sometimes, you know, we have a very cheap camera. We have a very cheap scene. The whole thing is that how I can finish something, how I can see something with let's say €5. So then you say that, okay, we don't care about Nyquist theorem, we don't care about aliasing, we don't care about computation. So there are lots of things that you don't care, because for you it is important to have a general view of something, right? You want to see whether you have, let's say in general, some black tones. Yes or no? I mean, it doesn't matter to draw the borders and so on. So you can then say that, oh, we don't care about the Nyquist theorem, we don't care about the aliasing. But aliasing, as I said, it happens if we are start sampling with less than the Nyquist rate, which means that we are doing the undersampling. Now here you can see some images for this aliasing issue in 1D. If we have a sinusoidal, which is in red, and if I sample with less than twice of the frequency, I have to raise it, with less than twice of the frequency that it had, what happens, I start to sample, but I am not covering all part of the image. In other words, if I give you the blue dots and if you connect them, what you will get is the blue signal, which is definitely not what we had in the red one. Now, same thing is happening inside an image. Inside an image, do you see these aliasing effects? You know, we had lots of nice breaks of a tower, and now when you take the image, you see things like this. In old TV, very old TV, I don't know if you remember, but your parents definitely could remember, this was very natural. I mean, seeing aliasing was like, oh, it's very cool, it's very normal. Like a movie without any aliasing, is it possible even? So we had lots of these things. So what happened is that now we try to formulate a way that we can get rid of it. We understand some of those things is we have lots of high frequencies and we have limitation because of the hardware, and nowadays we have the cameras which has very high sampling rate, so we don't care. Now, usually this happens if we have textures like this. If we have textures like this, as you can see, we start to have the potential of having aliasing, especially in here. Why do I have aliasing in here but no aliasing in here?
Because the frequency is higher.
Yes, because the frequency is higher in here. What is frequency? Frequency means change. So if you have lots of quick changes, it means you have high frequency. And if you have less changes or very slow changes, it means we have low frequencies. So if you compare here, we see that in one row we have 1, 2, 3, 4, 5, 6, 7, let's say, or 8 changes. But if you come here, in one row maybe we have, I don't know, 40 changes. So it means that here we have higher frequency than in here, right? So when we are using the sampling, we have to look at what is the frequency in here, because we look at the maximum frequency and we have to multiply by 2 and then do the sampling. So we have the, we can get rid of the aliasing. So this type of patterns that usually we have is called Moire patterns. Moire patterns are the patterns which we have lots of, let's say, parallel lines and lots of small blocks which are causing the aliasing, because the frequency is very high in here. The frequency is very high in here. So for this type of patterns, we have to have a very good sampling rate, or we have to use other techniques which you can see in here. One of the techniques that we are talking about is using low-pass filter. As Martin mentioned a bit earlier, it is happening, the aliasing is happening because we have lots of high frequencies. Like the camera is fixed, I cannot play with that one. many things that we have are fixed. Imagine that, okay, with the president, maybe he's a good president, and even you can like change the shirt. But if you go and make a movie of a lion in the National Geographic, you cannot ask the lion, can you please shave, because you have lots of high frequencies and so on. So you have to find out a way. And one way, as we said, that is using low pass filter. What low pass filter does is it kills the high frequencies. Now, question is that what should be the cutoff? Which high frequency we have to kill? How do I understand which high frequencies do I have to kill? Do I know which high frequencies I have to kill?
Based on the camera.
Yes, based on camera, I know what is my Nyquist rate. I divide it by 2, so I understand what should be the maximum frequency. So I understand the filter that I have should kill whatever is above that maximum frequency that I can actually handle. So I know what should be the cutoff frequency, and if I do it, if I use the low pass filter, what happens when I'm reconstructing my image, I have a very, very nice image of the breaks. Now, what actually happens, I have lots of missing of the data. Can you see the missed data in here? No, don't shake your head. I mean, if you can you please spell it out? We can't. We cannot see those details. So we can kill them because they will get rid of this aliasing. We won't have aliasing anymore, but we cannot see it. So in image processing, there is one term which we use it quite a lot. It's called psychovision. Psychologically, we are seeing the things. If we cannot see it, that's cool, so you can get rid of it, right? It's like that you have a zillionaire, and if someone comes and steals €1 from you, you will never understand it. But, I mean, that frequency for this image, if we kill those ones, we don't understand it because we have lots of other details and our eyes is not sensitive enough to do it. Now, so let's talk a little bit about how we want to do this interpolation in MATLAB, right? How we want to do the interpolation in MATLAB. If you know MATLAB, that's cool. If you don't know MATLAB, you see that we can represent lots of vectors or variables in MATLAB by using these terms. You can always look at them, look at the slides if it is important for you and you want to use MATLAB. We said that if you want to read an image, we are using imread command. We are using imshow if we want to show the image. I have given you lots of sample images I could, and those images, majority of them are color image, but we want to work with the unsigned integer 8-bit images. In other words, we have to convert it into grayscale. So we are using this command RGB to gray. And many of the operation that you want to do on an image is actually mathematical operation. Now, what happens is this. Imagine I have, I will give you the slides. The slides is available already in module. Assume that we have A and we have B, and both of them are unsigned integer 8-bit images.
It will be.
Okay? Now, imagine that this image has only 4 pixels. 0, 5, 250, and 15, 100, 200, 100, and 60. And what we want to do for some operation, and the rest what we want to do is we want to add these two. We want to add these two. 0 plus 100 is 100. 5 plus 200 is 205. 60 plus 15 is 75. 100 plus 250 is 255. Why? Because this is unsigned integer 8, this is unsigned integer 8, and the result will be unsigned integer 8. And which means that the maximum number that I can show is 255. So if I add 100 plus 250, although it's 350, but I cannot represent more, so it will be 255. So this is not good because you need to do some mathematical operation and you just want to make it unsigned integer at the end. So in order to be able to add them as a number, what you have to do, we have to convert the type from unsigned integer into double. So this is how we do it. So now you will see that your y or your double version of a and b are the same. If you add it, you will get the same number, except here it will be 350. And then you can look at the size of the image. Okay, this is wrong. It should be size. I will correct this one. It should be comment size. S is size of x, which tell you what is the size of the x. If the image is a color image, we will see that we will have 3 dimension. If it is grayscale, we see that we have 2 dimension. So my mistake, I will fix it. And then you see that we can use the for and if condition. This is an example which you can see. And in order to do interpolation, in order to do the zooming in MATLAB, we can use a command which is called imresize. Now, in imresize, you give your image, and then you will specify what should be the next size. If it is 64 by 64 and you want to make it 128 by 128, you say imresize x, 128 by 128. Or you can use a syntax like this. We can say that the output is imresize image x and 3. This means that make the image x 3 times bigger. So you can either specify what should be the size, for example 128 by 150, so it makes the image to be 128 by 150, or you don't know what is the size of x, but you know that you want to make it 3 times, 2 times, 10 times bigger, so you just put the number in there. And then in here we have an image, an example. We have an example, and what does it do? It reads an image and it rotates the image 180. If those of you who have taken this data analysis with MATLAB last semester, I think this was one of the samples that I saw within in the class. You have an image and you rotate it 180 degrees. Some important remarks is in MATLAB, unlike C and C++, you do not need to put semicolon at the end. And if you put only semicolon at the end, it means the echo will be off, but it is not the syntax. We can do lots of matrix algebra very easily in MATLAB. I think one of the best thing about MATLAB is that everything is very dynamic. Unlike C, C++, you do not need to know which variables you want to use, and you do not need them to define them. You can use the variable a, create it instantly as an integer. Next line make it a character. Next line making it float. So and then even you can delete it and kill it. You can use the whos command to see that which variables are used, and then there are some comments which you can use in order to clear the stuff. So today what we did, we talked about what is zooming, what is interpolation, how we are doing the interpolation. We have seen a few MATLAB comments. We have seen actually before that, we have seen what are the problems we have in the sampling, and which is the Nyquist problem, Nyquist frequency issue. Then we talk about the aliasing. And today, in the module, are all of you in the module?
No.
Please be a member of module.
No, but I'm not have your class
You
there.
have to go there yourself.
Yeah.
You just search. Oh, okay.
Search for digital image processing, and then it will come out. I will put your first homework in the module. Your first homework will be about this interpolation. Okay? You will have, I will tell you that some of the images that already are available in module, you have to use them to resize them by different techniques. And then you have to resize one of your own images. As usual, I will ask you to write a very short report, and the report is your own wording. your own observation, what you observe while you are doing it in English, and then you will also put your codes and some samples, and we will upload it. And Pejman, the assistant, is the person who will evaluate your homework. Okay? Now, we have talked about the zooming, which is cool, but now we will start to talk about something which is even more important, and it's called image enhancement. We will talk about different way of doing image enhancement, and then we will start a few examples of this image enhancement in details like illumination enhancement. Do you have any question? If you have no question, this is the end of the lecture for today, and be